Start recording. Okay, we are recording from beginning. Hello everyone, this is Lab 3, the Black Hole Lab from Alfonso for physics. So some background information that we'll need before we even get into the coding portion of the simulation would be stuff like the universal gravitation formula, momentum formulas, and then just some general kinematic formulas. So the universal gravitation formula would be the force of gravity equals gravity times mass 1 and mass 2 of a system. It works between two things only. And then you divide it by the distance between the two squared. And then if you need a specific direction of the force, you will multiply it by the negative r hat, or just r hat in general. But since we just need the magnitude for some of our coding portions later, we can just do without the multiplying by r hat, and that'll give us the magnitude of it. So momentum then is we can talk about momentum in respect to force. So our net force will be equal to the change in momentum over change in time, and we can further split that up into our net force is equal to the perpendicular component of the net force, and then the parallel component of the net force. And it's perpendicular and parallel in respect to the direction of momentum. And then position update, that's easy. RF equals RI plus velocity average times change in time. And that's what we'll be needing to use for like the spaceship and stuff. Okay, so now let's get into some results, which would be our Chrome tabs. So let's edit the program and look at it. So we have our seed, which is my GTID, which will randomize some of the components, but that's not important to discuss. We'll discuss some things that we had to put in. So we put in the general star mass that we all got. And then we started general upkeep of our formulas. So like velocity initial equals, why did I start with velocity? Momentum initial equals the star's mass times the velocity initial, and then momentum final equals the star's mass times velocity final. And then we can use that to find the change in velocity and change in momentum. So change in velocity would be velocity final minus velocity initial, easy enough. And then change in momentum is what we solved for here. We take momentum final and subtract momentum initial. And then calculating dp/dt is just change in time over change in momentum over change in time, as shown in the background slide. F net equals that, as shown in the background slide. And then general things. P hat equals P initial divided by the magnitude of it. And then we just keep getting components. Now we get the parallel component, and then later we solve for the perpendicular component right here. And then since we are solving for the mass of the thing, or of the black hole, we can do so by shoving in our formula that we use by shoving in every other unknown component and solving for the unknown component. So the mass of the black hole is equal to all the known components which we just solved for, which is the magnitude of the force times the magnitude of the star's position, and then squared, and then you multiply, and then you divide that by the gravitation constant times the star's mass, and that gives it to you. And then we can run the program, and then we can see the star's orbit around the black hole, and we can see the arrows showing, you know, how the force is changing the closer and further it gets. And then that gives us the magnitude of the net force, the magnitude of the parallel component and the perpendicular components of it. And then it also gives us the mass. And that mass is important because when we move on to part 2, which is the spaceship stuff, we need to put the mass here. Black hole mass. That's critical because the black hole is trying to suck up our spaceship and we don't want that. And so let's get to some upkeep. We have very big annoying things. But basically you just use all of those formulas there to get the net force on the planet, which would be the force acting on the force of the ship on the planet and the force of the black hole on the planet. Easy enough. And then all of these big things basically solve for the two components here, which would be the net force on the ship is just the force of the black hole on the ship and the force of the planet on the ship. And then we use position update formulas and velocity update formulas to very easily start, you know, changing its position. And then we can run the program and we can see. So in order for this to happen, we then need to, using those components that we do know, find some sort of initial velocity for the spaceship before its engines explode and stuff, for it to escape the black hole once it launches off the planet. And that was just me guess and checking the entire time until I got those two things. And so now I've discussed the results, we can look at what it means. So when we look at force in relationship to momentum, we can find that that a lot of them are equivalent mathematical statements in that the parallel component of the net force is equal to the parallel component of momentum, and the parallel component of the perpendicular component of net force is the perpendicular of momentum. But net force requires a known mass, and in our system we don't have a known mass for the black hole. So we use the rate of change of momentum since it does not require that, and we can use that to then solve for the net force. And so then our next thing is, what if we wanted the spaceship to orbit around the black hole like the planet did? And as per the fine print of the instructions, it's okay if we can't figure it out, which I did not. So it's okay. I barely found a way for the spaceship to escape without exceeding the speed of light. So we'll just imagine there were two orbiting objects, at least for my experiment. Thank you. That is all.